The world stands on the brink of a technological revolution, a revolution fueled by the enigmatic laws of quantum mechanics. These laws, which govern the smallest particles in the universe, are now being harnessed to create a new kind of computer. This new frontier is quantum computing, a paradigm shift that promises to reshape our world in ways we are only beginning to imagine. Unlike classical computers, which have been the backbone of our digital age, quantum computers operate on principles that defy our everyday experiences. Imagine a computer so powerful that it can solve problems in minutes, problems that would take classical computers billions of years. This is not just a leap in speed, it is a leap in capability. This is the allure of quantum computing. It promises to unlock new levels of computational power, enabling us to tackle problems that were previously thought to be unsolvable. Classical computers, the workhorses of our digital age, rely on bits. Bits are like tiny switches that can be either on or off, representing 1 or 0. This binary system has served us well, but it has its limitations. Quantum computers, on the other hand, harness the strangeness of the quantum world to process information in a fundamentally different way. They use qubits, which are not limited to being just on or off. They employ qubits, which can exist in a superposition of states, simultaneously representing both 1 and 0. This allows quantum computers to perform many calculations at once, vastly increasing their processing power. This unlocks unprecedented computational power. The potential applications of this power are vast and varied. Quantum computing is not just about speed, it is about tackling problems that are impossible for even the most powerful classical computers. These problems include complex simulations, optimization tasks, and cryptographic challenges. From drug discovery to material science, quantum computing could revolutionize the way we approach scientific research. From cryptography to artificial intelligence, quantum computers hold the key to unlocking solutions that have long eluded us. They could lead to breakthroughs in secure communication, machine learning, and more. Quantum computers hold the key to unlocking solutions that have long eluded us. This technology could transform industries, create new fields of study, and change the way we live and work. This is not science fiction, it is the future knocking at our door. The advancements in quantum computing are happening now, and they are set to accelerate in the coming years. The journey into the quantum realm is a journey into the heart of reality itself. It is a journey that will challenge our understanding of the universe and push the boundaries of human ingenuity. It is a journey that will challenge our understanding of the universe and push the boundaries of human ingenuity. As we delve deeper into the quantum world, we will uncover new insights into the nature of reality itself. Welcome to the quantum revolution. This is just the beginning of a new era in computing, one that promises to transform our world in unimaginable ways. To grasp the power of quantum computing, we must first understand its fundamental building block, the qubit. A qubit, or quantum bit, is the basic unit of quantum information, analogous to the classical bit in traditional computing. However, the qubit's capabilities far exceed those of classical bits, opening up a realm of possibilities that were once thought to be purely theoretical. Unlike classical bits, which are confined to a single state, qubits can exist in a superposition of states, simultaneously representing both 0 and 1. This means that a qubit can perform multiple calculations at once, vastly increasing the potential speed and efficiency of quantum computers. Imagine a light switch that is not just on or off, but can be in a state of both on and off at the same time. This unique property arises from the principles of quantum mechanics, which govern the behavior of particles at the atomic and subatomic levels. Quantum mechanics is a branch of physics that deals with the strange and often non-intuitive behaviors of the smallest particles in the universe. These principles allow qubits to exist in multiple states simultaneously, a phenomenon that classical physics cannot explain. Imagine a coin spinning in the air, neither heads nor tails, but in a state of uncertainty. This is a simple analogy to understand the concept of superposition. Just as the spinning coin is in a state of both heads and tails until it lands, a qubit remains in a superposition of states until it is measured. This is analogous to a qubit in superposition. The qubit can be thought of as a sphere, where any point on the surface represents a possible state. This allows for a much richer set of possibilities compared to the binary states of classical bits. It is not until we measure the qubit that it collapses into a definite state of 0 or 1. This process is known as wave function collapse, a fundamental concept in quantum mechanics. The act of measurement forces the qubit to choose a specific state, thereby providing a definite outcome. This ability to exist in multiple states simultaneously is what gives quantum computers their immense computational power. By leveraging superposition, quantum computers can solve complex problems much faster than classical computers. For example, they can factor large numbers, optimize complex systems, and simulate molecular structures with unprecedented speed and accuracy. Furthermore, qubits can be entangled, meaning their fates are intertwined even when separated by vast distances. Entanglement is another cornerstone of quantum mechanics, where the state of one qubit is directly related to the state of another, no matter how far apart they are. This phenomenon puzzled even Einstein, who famously referred to it as spooky action at a distance. This entanglement allows quantum computers to perform operations on multiple qubits simultaneously, exponentially increasing their processing capabilities. When qubits are entangled, the information they hold is shared, enabling quantum computers to tackle problems that are currently intractable for classical computers. It is like flipping multiple coins and having them all land on heads or tails in unison, even if they are miles apart. This synchronized behavior is what makes quantum entanglement so powerful and mysterious. It allows for parallel processing on a scale that classical computers cannot achieve. The difference between classical and quantum computing is not just a matter of degree, it is a fundamental shift in how we process information. Classical computers use bits as the smallest unit of data, while quantum computers use qubits, which can represent and process information in ways that classical bits cannot. It is like comparing a horse-drawn carriage to a spaceship. Both can get you from point A to point B, but the spaceship can take you to the stars. This analogy highlights the transformative potential of quantum computing. Both can get you from point A to point B, but the spaceship can take you to the stars. Quantum computers have the potential to revolutionize fields such as cryptography, material science, and artificial intelligence, taking us to new frontiers of knowledge and capability. Similarly, while classical computers have served us well, quantum computers promise to take us on an entirely new journey of scientific discovery and technological innovation. They hold the key to solving some of the most complex and challenging problems facing humanity today, from climate modeling to drug discovery and beyond. The future of computing is quantum, and it is a future filled with endless possibilities. Superposition, a cornerstone of quantum mechanics, is often described as a concept that defies our everyday intuition. It challenges the very foundation of how we perceive reality. In the quantum world, particles do not exist in definite states until they are measured. This means that until we observe them, they are in a state of flux, existing in multiple states at once. Instead, they exist in a haze of probabilities, a superposition of all possible states. This haze is described by a mathematical function known as the wave function, which encapsulates all the potential outcomes. Imagine a single atom being in multiple places simultaneously, or a light particle traveling along multiple paths at once. This is not just a thought experiment, it is a reality that has been experimentally verified. This is the essence of superposition. It is a phenomenon that is both fascinating and perplexing, pushing the boundaries of our understanding. This concept, though counterintuitive, is not just a theoretical curiosity. It has practical implications that are being harnessed in cutting-edge technologies. It is the bedrock upon which the power of quantum computing rests. Quantum computers leverage the principles of superposition to perform tasks that are currently impossible for classical computers. By harnessing superposition, qubits can explore a vast number of possibilities simultaneously, allowing quantum computers to perform calculations at an exponentially faster rate than their classical counterparts. This parallelism is what sets quantum computing apart. To illustrate, imagine searching through a maze. A classical computer would have to explore each path one by one until it found the exit. A classical computer would have to explore each path one by one until it found the exit. This process can be time-consuming and inefficient, especially for complex problems with many variables. A quantum computer, however, could explore all paths simultaneously, finding the exit much faster. This ability to process multiple possibilities at once is akin to having a supercharged problem-solving engine. This ability to explore multiple possibilities at once is what gives quantum computers their edge in solving complex problems. They can tackle tasks that would take classical computers millennia to solve, opening up new frontiers in science and technology. Superposition, therefore, is not just a mind-bending concept, it is the key to unlocking the potential of quantum computing. It represents a paradigm shift in how we approach computation and problem-solving. By embracing the uncertainty inherent in the quantum world, we open the door to a new era of computation, one that promises to revolutionize our world in profound ways. The future of technology, medicine, and even our understanding of the universe may be transformed by the power of quantum computing. As we continue to explore and understand the principles of quantum mechanics, we are not just expanding our knowledge, we are paving the way for innovations that could change the very fabric of our society. Embracing uncertainty is not just about accepting the unknown, it is about harnessing it to create a better future. Entanglement, another pillar of quantum mechanics, is a phenomenon so bizarre that even Einstein famously dubbed it spooky action at a distance. When two particles become entangled, their fates become intertwined, no matter how far apart they are. Measuring the state of one particle instantly determines the state of the other, as if they are connected by an invisible thread that transcends space itself. Imagine two coins flipping in perfect unison, always landing on the same side, even if one coin is in New York and the other in Paris. This is the essence of entanglement. It is a deeply counterintuitive concept, yet numerous experiments have confirmed its existence. In the realm of quantum computing, entanglement is not just a curiosity, it is a powerful resource. By entangling qubits, we can create correlations between them, allowing them to work together in a highly coordinated manner. This coordinated action is what enables quantum computers to perform operations on multiple qubits simultaneously, exponentially increasing their processing power. Entanglement is the secret sauce that makes quantum computing so potent. It is the invisible thread that connects qubits, allowing them to dance in perfect harmony, unlocking computational possibilities that are unimaginable in the classical world.